Good morning, class. We better get started. We have a lot of stuff to get through today. As always, let me start with some reminders. Um, you have a homework that's due today, homework 3. This is a quiz that's entirely on Canvas, and hopefully, I see that several of you have finished it. And if you haven't, please get it done today if you can. Otherwise, of course, you have a late day for tomorrow, like all homeworks. There's also a project milestone. Um, we for that you need at least one non-dummy um submission, and you need to submit a short report on Canvas. It's going to be like I expect no more than a paragraph or two. And this thing is, if you can view it in multiple ways. You can think of it as, for example, a way to revisit the code that you wrote for your previous homeworks. And I know that several of you have are viewing it that way, where you just use your existing code to run it on the new data, or if your existing code had problems, you can fix it and run it. We are almost, I think, done grading homework 1. We should be getting back to you soon, and that should also give you some feedback. So let me pause for questions. There's one. What do I mean by descriptive statistics of the data? Um, Basically, it's anything that you can use to characterize the data. For example, there's nothing specific here. I mean, you can choose not to do anything, but usually when you're given a new data set, rather than throwing algorithms at it upfront, you need to kind of look at the data and get a sense of what does the data look like. For example, as an example, what's the most common label? What happens if you predict the most common label all the time? And Another thing would be, what's the dimensionality? Any sort of descriptive details. For instance, in this particular data set, there are multiple feature sets, right? So you get one of those feature sets is actually, in some sense, human readable. It's not just a bunch of vectors. So can you, show any interesting information about those features that give you insights about those? Can you show any interesting insights about all those attributes that I provide, like age and all that, that would give you insight into, say, designing features or choosing a model? Or like, is there any sort of obvious correlations that you can spot that automatically gives you uh, that quickly takes you towards a good classifier, a good learning algorithm, or anything of that sort? This is as I mentioned to someone also uh, in uh, in Canvas. Uh, Maybe it was anyway. As I mentioned in a discussion on Canvas, the I'm deliberately keeping the project open-ended. It's meant to simulate the situation where you're just given, you are a data scientist and you're given a data set and you're told, I need a machine learning solution. What do you do? So you have to kind of try different things. You have to kind of look at the data, get a feel for it. And this is uh, almost uh, a bit of an art. And uh, what I'm asking you to do right now is to essentially look at the data, but of course you can't look at all of it. So you need to summarize it in some way so that you can kind of get some insights into it. We won't be covering that stuff in this class, but if you want to talk about any ideas, come to office hours and I'll be happy to chat about it. So other questions? Yes. So if the perceptron keeps making a mistake, then what can be done to prevent it? So let me just take a look at the quiz question, just so that I don't unnecessarily just give you the answer. Right. So, okay, so Parth, what was your question?
Yes, so my question was mainly for the question 12. I was wondering if the perceptron keeps on making the mistake, then how can you approach or make it better? Is there any way where you can make it better? Or
So you
it seems
probably
like,
go on.
yeah, it seems like if keeps on making mistake, it means that it's not linearly separable, which in that case, it's not possible to run through
So
the
think
perceptron.
about think about your homework, and in fact, revisit the lecture that talks about what can you do if your data is not linearly separable. Um, it may not be linearly separable with these features, but could you do something else? Or can you do? I don't want to
Right. Yeah.
uh, you know give away the answer, but in some sense, some version of the answer is in the lecture that talks about what to do when in the class in the lecture around linear classifiers, where we introduce linear classifiers.
Mhm. Okay.
So I'm going to kind of be a little bit less open about answering that.
Okay. All right. Thank you.
Is there? So there's another question about the project. Is there any way we can know which method, decision tree, or perceptron, etc., the high scores are achieved with in Kaggle? Um, so I think Kaggle allows you to tag um your submission as which algorithm is used. But honestly speaking, I don't know what Kaggle shows to you when you are logged in. Um, if you want to kind of exchange ideas, I would suggest use the discussion board on Canvas. Um, I mean, it's not really a competition, so feel free to kind of exchange ideas on this at the level of, I tried this and it worked. I tried this and something's not working. Can someone help, or things like that. I'm not entirely sure how to control what Kaggle does and does not show about the high scores, because that's something that that that's out of my control. There's a question about question 21 on the quiz. Go ahead. If you can type it, or you can say it.
Hello, sir. This is Shrija here. I have a question on the same one. I only asked it. So basically,
Yes.
I'm kind of confused, but they've given a truth table and they're asking you to find the margin. So,
Yes.
uh, like, do I find a line and then just take a distance of each point from it, or?
Yeah. So remember, there are two things. So there is okay. I can. So there is margin of a data set with respect to a line or a hyperplane, and then there is the uh, this is the distance. Actually, the minimum. It's the minimum distance of any point in the data to the separator, right? So let's name this as, say, let's give this thing a name. Let's call this mu. I've forgotten what notation I use, so I'm just making things up. The margin of a data set and
I
a line,
guess.
something like that. Okay.
Mhm.
Um, but this is with respect to a particular hyperplane. What the question's asking is the margin of a data set. There's another related thing, which is margin of data set is the maximum margin of the data set with respect to a hyperplane among all possible hyperplanes. So essentially what I'm asking here in this question is, try out every possible line you can think about that separates the data.
Oh, okay.
And because it's two dimensions, there's a very, you can plot all the points there, and you'll get a very clean visual intuition about how the line should be positioned so that you achieve this maximum.
Mhm. Okay.
And you can try to prove it formally if you want. I mean, this is a multiple choice question. I'm not looking for anything but the answer. You can think about how to prove, how would you solve this problem if you had to solve it analytically. there is actually a way of solving this problem analytically. Sorry, not analytically, algorithmically. But I don't want you to, I mean, feel free to think about it, but because it's 2 dimensions, you can just visually inspect it, and the intuitive answer is actually correct.
Okay, sir. Okay, thank you.
Okay, cool. So are there any other questions about homeworks or quizzes or such, or the project or anything? If not, I also wanted to kind of pass on an announcement that was sent to me. There's going to be some sort of a tech symposium on Wednesday, October 28th. That is, I think, about 2 weeks from now. This is the Public Interest Tech Symposium, which is some combination of digital technologies and public interest, and it's open to everyone. If you're interested, just you can search for the name or go to search for UI2 Symposium, and maybe it's going to be interesting and open. It will probably talk about challenges that we have to deal with as technologists when we are talking about public interest technologies. So yeah, this is primarily informatics style thing, because the UI2 is the Utah Informatics Institute. All right. So with that out of the way, let's go back to the main course. We were talking about we were talking about computational learning theory, and we were just getting started with what does the Occam's razor theorem that we proved on last Thursday tell us. So just to kind of make sure that we're all on the same page, we're talking about computational learning theory, and we are roughly right here. We looked, oh no, we are in the next one. In the last lecture, we looked at the definition of pack learning, and we looked at one theorem that we called Occam's razor. That said, if you have these many examples, then with high probability, there exists, we can find a classifier that that achieves low error. So now, given that, so it's essentially what the theorem gives us is a tool. The question now for today's lecture, for the first part of today's lecture, is given the tool, what can we discover? So we'll look at some positive and negative learnability results. We'll look at a few examples where we kind of just apply that theorem directly, and then I'll list out some more results, and we'll see where it goes. We looked at this conjunctions in the last lecture, so I'm just going to quickly refresh our collective memories around this, and then go ahead. So just to remind you, the Occam's razor theorem that we proved tells us that if you have these many examples, m, if the number of examples m that you have is more than 1 over epsilon times log size of h plus log 1 over delta, then with high probability, with probability greater than 1 minus delta, we can find a class. There exists a classifier whose error is less than epsilon. This is what we saw in the last lecture. Now, remember, the definition of pack learning is really asking us to say, if this complexity here, if the sample complexity is polynomial in 1 over epsilon, 1 over delta, size of h, and the dimensionality, here I'm using n for dimensionality. If the number of examples you need is polynomial in all these things, then we call that concept as pack learnable. Now, it's just saying, does there exist a classifier that with these m examples can achieve error less than epsilon? And is it possible that we can find it? So using this, now we can apply this question to we can ask this question of specific sets of functions, whether it is pack learnable or not. So the first function that we are looking at, in fact, we looked at in the last lecture, is general conjunctions. Conjunctions are, just to remind you, functions of the form something and something, just a bunch of literals. These are called literals. which is a variable or its negation, or well, a literal is a variable or a negation. And a conjunction is just a bunch of literals that are connected with an AND. So we saw in the last lecture that the number of conjunctions in n variables is 3 power n, and log of that quantity is n log 3, which for our purposes, we don't really care about the log 3 part, but for our purposes, it's important to note that this quantity is linear in n. Because it's linear in n, the sample complexity, the number of examples needed for this epsilon delta guarantee, is linear in n. It is linear in 1 over epsilon. It's logarithmic in 1 over delta. So essentially, all of these are polynomial. This means that the number of examples needed is polynomial. Number of examples needed to find, sorry, if you have these many examples, then you can find a classifier. There exists a classifier whose error is less than epsilon, and the probability that you can find such a classifier is more than 1 minus delta. So this means that general conjunctions are pack learnable. There's a question: does the definition of pack learnability also require that there should be a polynomial time algorithm in 1 over delta and all these things that can produce a sufficiently approximate hypothesis? The answer is not quite. There are two versions. There are two kinds. In general, yes. So in general, the definition of learnability requires this, but we split the definition into two parts. We split the definition into pack learnable, which means does there exist such a thing? Are m examples enough to kind of discover such a hypothesis? And then there's a second part which talks about the computational complexity. Can you find such a hypothesis in a reasonable time, in a polynomial time, in all these things that actually achieves this approximation guarantee? So this means that you have two criteria. You have the sample complexity, which is an information theoretic criterion, and then you have the computational complexity, which talks about, can you actually find it? Is that the first part is, are m examples, do m examples contain enough information to distinguish one hypothesis? And the second part is, can such a hypothesis be found in a polynomial time? There's another question. M is in log delta, it's log 1 over delta. It's not exactly polynomial. It is polynomial. In fact, log grows slower than polynomials. So it's any function that grows slower than polynomial is considered polynomial because we just need the big O notation. In the order of in order of magnitude, it's less than polynomial actually. So that's still good. Anything that's less than polynomial, less than or equal to some polynomial is good enough. Does this assume that the examples are noise-free? Implicitly, for now, we have made that assumption. We have made that assumption because we are assuming effectively that the hypothesis class that the learner is exploring is either equal to the concept class or the hypothesis class contains the concept class. What that means is the learner can find for any sort of a function that nature might choose, the learner will find a good approximation of it within that set. This implicitly means that nature does not get to add noise. You can think of noise as a function. Nature does not get to add noise, which means that it has effectively we are in the noise-free setting. So in the last lecture, we went through some interpretations of what this means. I'm not going to revisit it, but I've been told this is these examples are pretty helpful, and personally, I found it to be very helpful when I or some version of these examples when I first encountered these ideas. What do epsilon and delta mean? Just to kind of briefly talk about it, epsilon is how accurate do you want your classifier to be, and delta is controlling what's the chance that you'll actually find such a classifier. And these are two separate things. There is the accuracy of a classifier, and then there's the guarantee of finding the chance of finding such a good enough classifier. That's why it's probably approximately correct. So this is the probably part, and this is the approximately correct part, and this is the probably part. Okay, so in the last lecture, before my slides abruptly disappeared, we started looking at 3CNFs. 3CNFs are functions where the CNF stands for conjunctive normal form. Not form, I'm not going to write form. Basically what it means is that the Boolean function is a conjunction. You know, if you look at it, forget everything inside the parenthesis, it's a conjunction. But it's not a conjunction of just literals, but it's a conjunction where each component here is itself a disjunction. So a 3CNF specifically allows an arbitrary number of conjuncts. These are the conjuncts, but every conjunct can have at most 3 literals. A literal, remember, is either a variable. I can't spell variable, so I'm just going to write xi, or it's negation. So you should have 3 things here, or 2 things, or 1 thing, at most 3 things, and they are all connected by a disjunction. You collect a bunch of that, and you connect all of these conjuncts, these blocks, with a AND. So this is a 3CNF. It's a, the reason this is used as an example is because this is a well-studied class of functions in many parts of formal computer science. So then the question is this class of functions learnable? Once again, we can ask this, we can apply the same idea. The hammer is essentially the same. We have a hammer here. Hammer is asking us, okay, if I want to talk about learnability, first we're going to talk about sample complexity, which is to say, how many examples do you need to guarantee packed learnability? Just really, what do we need? What is the smallest value of n? For that, we don't get to control epsilon and delta because those are like the parameters to the situation. The only thing that we want to compute is the size of the hypothesis class. So really, when we talk about sample complexity here, we are really talking about what's the size of the hypothesis class? How many 3CNFs are here? So this is somewhat involved, slightly more involved than counting the number of conjunctions, but it's not terribly complicated. To look at this, first of all, notice that the 3CNF is just a big conjunction, right? It's just a conjunction because we have a conjunction of all these things. It just so happens that these things here are slightly more complicated. So first, let's count how many of these conjuncts exist. Each conjunct in a 3CNF is it looks something like this. It has exactly 3 spots. In each spot, either you can put a variable, or its negation, or you can choose to leave it empty because we have at most 3 literals, or empty. So I think I've this. Oh, right. We can do it that way, but a better way of doing this is we have 3 spots here. Really, we can choose 3 variables, or we can choose 2 variables. Instead, imagine that we have this big bucket, x1, not x1, x2, not x2, and so on, xn and not xn. This bucket has 2n things. Out of these 2n things, we want to select 3 of them, maybe this, and maybe this. And maybe the third position, we choose nothing, up to 3 of them. So really, we have 2n, choose 3, plus 2n, choose 2, and so on. Right? We can choose 3 things in 2n, choose 3. We can choose 2 things in 2n, choose 2. We can choose 1 thing in 2n ways. We can choose nothing in 1 way. add them all up, and all of these things very, very loosely are order of 2n cubed. So we're going to just upper bound everything because we only care about whether it's polynomial or not. So all of these things together, so we have 2n choose 3 plus 2n choose 2 plus 2n choose 1. So among those 2n literals, there are n variables, there are 2n literals. Among those, we can choose 3, we can choose 2, we can choose 1, or we can choose none. All of these are really order of 2n cubed. Which is what the number of conjuncts is. So this is really, so far, all we have done is talked about how many of these kinds of objects exist. Now, the next step is we're going to glue them into a big conjunction. That's easy. We're going to select many of these and connect them into a conjunction. So a 3CNF is just a conjunction of these many variables. We know how many conjunctions there are, the number of conjunctions. So either for every one of these things, either you choose it or you don't in the conjunction. So you have these many slots, you have order of 2n cubed slots, and we're building a conjunction. In every position, we can either put this literal or not. So there are two options. So either the literal goes here, sorry, not the literal, the conjunct goes here, or empty. These are the two options for every step. And there are 2n cubed such positions that we can make these choices. So the number of 3CNFs is 2 power 2n cubed. That's the size of the hypothesis space. This is, I mean, of course, this is not the exact number. This is just order of magnitude, but that's all that matters. We notice that I've been making rather gross approximations here with, talking about these things. We don't care about the exact number. So what this means, but this gives us all we need. So the number of 3CNFs is order of 2 power 2n cubed because we have 3CNF. And that means the log of this quantity is roughly order of n cubed. It's a polynomial, and it's a cubic polynomial, right? So because it's the log of 2 power 2n cubed is order of n cubed. So can I explain why n cubed? Because, so if you got 2 power 2n cubed, let's take its log of 2 power 2n cubed is, I'm going to take log to the base 2 just because it's multiplying. Otherwise I have to keep a log 2 around. So this is 2n cubed, which is 8n cubed. 8 is just a constant, so it's a cubic polynomial. This just says it's cubic or less. So that's what it is. From the previous part here. Oh, from here. So this quantity here is what makes it cubic. We can essentially ignore all these. We can essentially ignore everything here. So if you look at, so I'm going to make that. Let me actually make it a new page so that. So you have this quantity here. Let's only look at the first term because that's the only thing that really matters. So you have 2n choose 3 is 2n times 2n minus 1 times 2n minus 2. Well, let me write it more. It is 2n factorial divided by 2n minus 3 factorial times 3 factorial, which is 2n times 2n minus 1 times 2n minus 2 divided by 3 factorial. I mean, effectively what we get is this term behaves like 2n. When n is large, that the constants really don't matter. This also behaves like 2n. This is essentially behaving like we are multiplying 2n 3 times. So you have 2n times 2n times 2n. When n is large, the 1 and 2 really don't matter. This assumes that n is greater than 3. Yeah, I mean, in the big O notation, we assume it's fine. It doesn't matter. N has to be greater than 3 because otherwise this term is not even going to come up. We can't choose 3 things out of fewer than 3 things. So this is not equal to, but this is I'm going to say in the same order, in the same complexity, which is 2n cubed. Does that answer your question, Han? So there are a couple of other questions. What conjunct is 2n choose 0? That's just true. It's just saying that nothing got picked. So in this case, yeah, it's false because you have a or here. The identity for false is or. For conjunction, it's true. For disjunction, it's false. Because you're not picking something, and if you don't, essentially, the way to think about disjunction is: are any of these things true? If you have none of them, nothing is true. So it's false. Okay, so let's go back to where we were. Oh, actually, I take it back. So this is we're not talking about the underlying things. When it's not a 0 CNF. Yeah, okay, you can call it a 0 CNF. Sure. I mean, I don't know what the name tells you, but okay. So the important point here is really that the size of the hypothesis space is order of n cubed. We can plug that in here, which means the number of the log of the size of the hypothesis space is polynomial, which means the sample complexity m is also polynomial, which means 3CNFs are packed learnable. For packed learnability, for the complete definition of packed learnability, we also need to invent an efficient algorithm that can find a consistent hypothesis. And I'm not going to tell you how to do it. It's kind of fun to think about how this would work, and it's an interesting exercise. So I'll leave it for those of you who are interested. Let's now look at another class of functions: general Boolean functions, all possible Boolean functions. So far, we've seen conjunctions and 3CNFs, and both of them turned out to be packed learnable. For conjunctions, the log of the size of the hypothesis class was order of n. For 3CNFs, it was order of n cubed. Let's now get ambitious and go to all possible Boolean functions. So how many Boolean functions are there with n variables? And I forgot to put this up in a poll, so maybe you can just say this in chat. We've covered, we've talked about this a couple of times before. So how many functions are there? So the way to think about this is a Boolean function is basically a function that's assigning the last column of a truth table. So imagine you have x1 through xn. Imagine you're filling out the truth table. Every way in which, and let's say this is the function y, you have, I'm not going to put circles, instead let me use just shade. So every way, you have 2 power n rows in any truth table. And every assignment that you make to this last column gives you a different function. In every position here, you can either put a 0 or a 1. And there are 2 power n such things. So you have 2 power n. And those of you who answered that are right. So there are 2 power n Boolean functions with n variables. The log of that quantity is still 2 power n. So log of the size of h is exponential. general Boolean functions, this means, are not pack learnable. This is the second time we have encountered this result. If you're keeping track, just looking at it in different ways. So the log of the size of the last time we saw that was in the context of the halving algorithm. So the log of the size of the hypothesis class is exponential. General Boolean functions are not pack learnable. Now let me just go through a list of functions that are just, these are named classes of functions that are all pack learnable. We've already seen 3CNF. KCNF is just a generalization. Instead of 3 literals inside each block, you have at most k. So that's a KCNF. There's another thing called a K-class CNF, where you have a conjunction of k things. So you have, for example, a 2-class CNF would be something and something else. And inside this, you can have any number of literals. It doesn't have to be the same. So let me, oh, not all. And so on. So this is a K-class CNF, and I want you to think about how many such functions are there. The log of the size of this thing is order of kn, it turns out. And then there are KDNFs, where you just swap the and with or in the KCNF definition. And then there are K-term DNFs, which are disjunctions of at most k conjunctive. Oh, actually, no. DNF is, yeah, a K-term DNF is exactly like this thing. So you have something or something else. So this is a 2-term DNF. And then inside this, you can have maybe x1 and x2 and not x3 and x4, or maybe x1 and not x5. This is a 2-term DNF because this is a term and this is a term. It's a D for disjunction, DNF, because this thing here is a disjunction. So these are just classes of functions. I mean, if you don't really care about this, don't worry about it. But this is leading up to an interesting point, so we'll get there eventually. There's a quick question: can't you represent all Boolean functions with 3CNFs? The answer is no. As we just showed, the number of Boolean functions is much more than the number of 3CNFs. So that means that there must exist some function that is a Boolean, some Boolean function that is not a 3CNF. In any case, so you have these 4 classes of functions. The short answer is, the short version of the result is, all of these classes can be learned using polynomial size, so polynomial sample size. That means that the sample complexity is polynomial in the number of variables there are. And if you want something to keep you busy in an afternoon, try to prove all of these. They're not too hard. They kind of follow the same template of proof that we saw for 3CNFs. But the more interesting part is, suppose, so let's look at this specific thing. Suppose we have a 2-term DNF. We can ask, suppose I know that nature is choosing a 2-term DNF to represent its function, represent the true concept. So how should our learning, what should our learning algorithm, what set of functions should our learning algorithm explore? Now, this seems like a naive question. So nature has chosen to represent its function as a 2-term DNF. It almost seems like a hypothesis class should also be a 2-term DNF. If we know that information, why not just use it? So if you want to learn a 2-term DNF, it may seem obvious that we should explore the set of 2-term DNFs. Unfortunately, there's a sort of a counterintuitive result here. Even though the sample complexity is polynomial for this set, the computational complexity is not. So that means that if you, essentially what that means is a polynomial number of examples can help us uniquely identify a 2-term DNF that has low error with high probability, but finding that function is going to be computationally intractable. This is one of those sort of weird results. Effectively, what this means is that determining whether there is a certain 2-term DNF that's consistent with the training data is NP hard. it's intractable computationally. In other words, even though k-term DNFs, K2 is just a special case, but even though k-term DNFs are back learnable in the sample complexity sense, there is no efficient algorithm that can explore that space. And this is kind of weird. I mean, there's this space is essentially complicated enough that exploring it would require more time than is reasonable. But we have seen an algorithm for KCNF. I mean, we didn't see it. I left it as an exercise, but there exists an algorithm for learning a KCNF, 3CNF. And there's another interesting thing. The set of all functions that are KCNFs is a superset of these k-term DNFs. A k-term DNF might look something like this. You have a term or another term. It can be rewritten into this form. This is a technical detail. If you want to see an example, this is a term A and B and C. This is another term D and E and F. You can expand the parentheses and apply the distributive law, and essentially you take one pair of things from each bracket and glue them together with an OR and connect all these things with an AND. So this becomes a 2CNF. This is a 2CNF. This is a 2-term DNF. Every 2-term DNF can be represented as a 2CNF. And there exists some efficient algorithm for a 2CNF. This is kind of weird. Exploring this set is intractable. Exploring a 2-term DNF is intractable, but exploring KCNF is tractable because there exists an algorithm. What's happening is this concept class of k-term DNF, even though if your learning algorithm is going to search that exact set, it's computationally intractable. If you search a larger set, so if this is your k-term DNF, the statement KCNF is a superset can be seen as this picture here. If this is k-term DNF, this is a set of KCNF. What essentially the message of the slide is saying, there is this set of functions, a small set. I mean, polynomially not, only a polynomially large set, or rather the small in terms of sample complexity. That's the k-term DNF. It's a small set, but exploring it is intractable. If you really want to explore this set, don't bother exploring the set 3. Instead, find a superset of it, or not take a specific superset, in this case KCNF, and search the larger space. And you can efficiently search this larger space, and thereby you will find this classifier that you're looking for because it's contained in it. So effectively, this is an important point. Even though the details here might be a little bit confusing, the larger point here is sometimes a concept cannot be learned using one representation, but by swapping a representation, going to a more expressive space, you might be able to successfully learn. We've already seen this before. We've already seen this before with linear classifiers. Learning certain classes of functions was intractable if you explore the Boolean set, but by going to the larger class of linear classifiers, you can efficiently learn. We saw that in the context of online learning. This is the batch learning version of a similar sort of an unintuitive result. There's a set that is small and hard to explore. And in order to search that set, you go to a larger set and explore the larger set, and you will end up solving the smaller thing, which is, this is a mildly unintuitive result. And if you're interested, I can point you to the reference that gives you that gives you the proof. So this is a very strange result. Yes, and I mean, I don't have a good intuitive understanding of this, so I'm not going to make an attempt. As far as I'm concerned, I have reconciled myself to the result. This is the world we live in. This is the weird properties of these functions. One way of thinking about this is these these things happen in this sort of unintuitive things can happen in combinatorial spaces, because learning in this case is search, but more specifically it's combinatorial search. And similar sort of phenomena happen when, for example, you are exploring the space of I don't want to talk about integer programs in too much detail, but um, the 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 problem with this sort of a situation happens when you have when you're trying to solve integer programs as well. When you make the space more constrained, when you make the search space smaller, things can get harder. But there is a misconception in the comment that says all Boolean functions. Oh no, actually, this hasn't had to do with all Boolean functions being back learnable. All Boolean functions are, of course, not back learnable, but this is all about computational complexity, not about sample complexity. All Boolean functions are not back learnable, even from a sample complexity point of view. This is a discussion about computational complexity. In fact, that's an excellent segue into the next point, which is we're going to talk about negative results. There are two kinds of negative results when it comes to back learnability. The first one is a kind that we just saw, computational complexity. It shows that these results show that certain concept classes cannot be learned because of the computational complexity of learning. It essentially takes these kinds of results take the form: a concept in this class C cannot be learned unless P is equal to NP. Or another way of thinking about it is a concept in this class, learning a concept in this class is NP hard or NP complete or something like that. Essentially, it's intractable to search the space. Another kind of result is an information theoretic non-negative result that says the sample complexity is bad. Essentially, it says that the concept class is so rich in terms of information that only a polynomial number of examples would not be sufficient to distinguish one concept class. And usually for this, you can the proof would involve counting the number of functions and showing that the number of functions in that hypothesis class is too large. You should think about whether this is always a problem. You may be able to kind of make some approximations, change the definitions a little, and move around. So let me list out a few negative results from the complexity theoretic point of view, namely from the computational point of view. K-term DNF, we just saw that in a little bit more detail. K-term DNFs are intractable to learn from a time complexity point of view. There's this curious result from, I think, the 80s or maybe early 90s that talks about neural networks of a particular architecture with just 3 nodes cannot be learned if you are only exploring that space. There are certain classes of functions called read once Boolean formulas, and if you involve any quantifiers like universal quantifiers or existential quantifiers, computational complexity prohibits us from learning that by exploring just that space. From the information theoretic point of view, we already looked at a proof of this. Arbitrary Boolean functions cannot be learned. The sample complexity is too high, it's exponential. Those of you who are familiar with deterministic finite automata, these cannot be learned. Or alternatively, if you've used regular expressions are equivalent to DFAs. So regular expressions cannot be learned. So context-free grammars cannot be learned. These are information theoretic bounds. The number of examples needed to learn them is exponential. So this is the end of this particular unit, and I'm not actually while I'm switching slides, I'll pause for a few minutes, a minute or two for questions. So, okay, yes, so there is a question: if the sample complexity is too high, then it is not back learnable. That's right. In some sense, it's the definition. The pack learnable means the sample complexity is polynomial. It's just we are calling, and keep in mind, this is a definition that that we have chosen is interesting. You can say that, yeah, this definition is meaningless, but we have decided that this definition is interesting, and it already tells us it gives us some valuable insights. The computational complexity is an extra layer. So there are two kinds of complexity results, which there's sample complexity and computational complexity. For pack learnability, if you remember the definition of pack learnability that we saw last week, there is pack learnable, which is essentially the number of examples is polynomial, and there is efficiently learnable, where the time is polynomial. Together, these two things together define whether a concept class is pack learnable. So there are a couple of questions that are actually pretty interesting. So there's one that says, so neural networks with 3 nodes cannot learn, but greater than and less than can. Not quite. This is essentially saying there exists at least one neural network that does not learn. In particular, here's a construction. It's proved by construction. And if you have greater than 3, you can always kind of make those 3 things dummy nodes that do nothing, and essentially that would work. So from a complexity theoretic point of view, neural networks cannot be learned, but in practice, as we will see, neural networks are doing quite well. So this is, in some sense, a good point, because there's a mismatch between our understanding, our theoretical understanding of machine learning, and what we are observing in practice. The stuff that I'm seeing, that you are seeing today, is the theory of machine learning from the, say, 80s and 90s that kind of went all the way into the 2000s. Something interesting happened around 2012 and going from 2012, which is neural networks started working, and they started working remarkably well. And if one of you wants to make name and fame in machine learning, or at least in this little niche of machine learning, come up with a better theory. Essentially, what we have here is theory that is not quite matching up to experimental observations. So we need better theory. So there's another question: aren't all functions like neural networks and perceptrons and such things not pack learnable? And I'm assuming, Brett, what you mean by that is there are an infinite number of functions, and as a result, of course, it's not going to be pack learnable. Currently, we are operating under the hypothesis that there is we are in the finite in the set of finite functions. There is a technical detail inside this, which I can point you to the paper, which we can talk about. But perceptrons, neural networks, all linear classifiers, as things are essentially, there are an infinite number of them. So we will have to update this theory to include that. So we'll have to basically change the dependence on the size of this H to something else that behaves similarly for infinite sets of for real valued classifiers. There's another. We do not know what the concept class is. How do we know its computational complexity or sample complexity? In fact, Han, your question could be applied to sample complexity also. This is another thing that we have essentially assumed away. For now, I'm assuming that we know the concept class and the hypothesis class contains it. Literally, the next thing that we will talk about is, what if we don't know the concept class? What can we say in that case? So we'll get there. That will take us into this. That's why it's called agnostic learning. We are talking about learning where the learner is agnostic of the concept class. The last question. So not learnable because of information theoretic means the sample needs to grow exponentially. Yes. Not learnable because of complexity theory means the time is exponential, effectively. Yeah. Or rather than exponential, I would like to say not polynomial, because you can have super exponential in such things. You can have functions that grow faster than exponential. All right. So Let's now kind of expand our definitions of this, not definitions, expand the scope of situations we are considering with this notion of agnostic learning. So so far, what we have seen is the general setting for batch learning, and we've seen pack learning, the definition, and Occam's razor. Essentially, this allows us to answer the question, how good will a classifier that's consistent with the training set be in the future? The important thing is we assume that we can find that we're assuming that the classifier is consistent with the training set. So there are three assumptions that we have made so far. The training and the test set come from the same distribution. This is the assumption of fixed but perhaps unknown distribution over the examples. We've also assumed that the hypothesis space is finite. And finally, we've assumed that for any concept that nature gets to choose, there's some function in the hypothesis space that's consistent with any training set. What we will do now is let's look at this last assumption and effectively get rid of it. This takes us to this notion of agnostic learning. We assumed so far that the learning algorithm could find a true concept. When I say true concept, I mean it can find a classifier that perfectly labels every example in the training set, for example, like your decision tree. So what that means is the hypothesis space that the learner is exploring fully contains the concept set, the concept class. Or equivalently, using the same using the words of Han from the chat, we know the concept class because our hypothesis space contains it. What if we don't know the concept class? If we don't know the concept class, what might happen is we are searching for a function in a certain space, but we have no idea whether the true function lies inside that space or not. In other words, C is not a subset of H. So we don't know C, so we are going to essentially stop thinking about C anymore. This setting is called agnostic learning. The learner is agnostic to the true concept class. And this is a more realistic setting because in reality, we never know whether, what set of functions nature uses to decide, say, for example, whether a photograph contains a cat or not. So this is a more realistic setting. And so we can ask the same question. Can we say something about sample complexity? The first thing to think about is if we are learning a concept class using a certain hypothesis class, but the true function may not be in it. If that happens, we are not even guaranteed that the training error will be zero, because it's entirely possible that not a single function in the set of functions we are exploring correctly predicts every example in the training set. So the training error need not be zero. All we can do is we can find a classifier that maybe has a low training error. Maybe we can find a classifier that has the lowest training error, but that's the best we can do. So just to remind you, the training error S of a classifier, is the number of examples in the training set. S is your training set, the number of examples in the training set where f of x is not equal to h of x. H of x is what the hypothesis believes the label to be, and f of x is the ground truth, the true label for that example. So the error is the number of examples divided by the number of examples where there's a mistake divided by the number of examples you have. So it's the fraction of examples that are misclassified. This is the training error. It's something that we can calculate given the hypothesis. So we can, of course, find a classifier that has low training error, but we don't really care about low training error. We want a classifier that has low generalization error. Or rather, or equivalently, we want a classifier that has high accuracy on future examples that are unseen. So let's briefly summarize what we have. This is a quantity we can measure. This is a quantity we can measure, and we can also find classifiers that make that quantity small with some caveats. We'll get there eventually. But we don't care about that quantity at all. What we want is to make the probability of future errors small. So the question that is going to concern us is the following. If I know that this is small, how many examples do I need to, what should M be, for me to guarantee that this quantity will not be too far off from it? So if the empirical error is small, or it doesn't even matter small, how far off can the generalization error be from the empirical error? To answer this question, we'll be using the notion of tail bounds, which talks about how far a random variable can get from its mean. So hopefully most of you have seen the notion of tails of distributions, where we are asking, how much of the probability mass is far away from the mean. So this takes us into this sort of a segue about bounding probabilities. There's a very good question in the chat. Wouldn't this assume that we have some knowledge of the distribution? That's where we are kind of bound. We can't assume anything about, we can't assume any knowledge about the distribution, and yet we want to bound the tail. And we'll see how to do that. It's a kind of, it's really a cool a cool way of analysis. So I'm glad you asked that question. So we are not going to assume anything about the distribution. Let's kind of build up towards that. Let's start off with something simple. From the law of large numbers, we know that empirical means converges to the true expectation as we collect more samples. So if you have an unknown coin and you want to estimate the probability of getting heads, you can toss the coin many times, m times, and you can compute the fraction of number of heads divided by the number of tosses. And this fraction will get closer and closer to the true probability of heads as m increases. As m increases, we get a better estimate. But what we really want is not exactly this idea that things converge, but what we want is, what is the gap? If I have only m tosses, how far off is this fraction from the true probability? What can we say about the gap? And the nice thing about these gaps is there is actually a fair amount of literature in the probability and statistics world that that's going to help us. Hopefully, some of you, not all maybe, but hopefully some of you have seen these kinds of inequalities. Markov's inequality tells us how far off can a random variable x be from some value a, any value a, and or what's the probability that x can exceed some value a. And it says this probability decreases as a increases. It's the mean expected value divided by a. Chebyshev's inequality says what's the probability that a random variable, the difference between a random variable and the mean, is more than some number of standard deviations. This quantity is less than 1 over the number of standard deviations squared. Hopefully some of you have seen this, but unfortunately neither of these are directly going to help us. Neither of these tell us specifically what we care about, because we want to bound the sums of random variables. The training error depends on the number of errors in the training set. So it's essentially the sum of a collection of random variables, where every random variable is this going to be an error or not. So it's a mean, actually. It's an empirical mean. The tool that we will use is this idea called Heffding's inequality. Sometimes they're also called Chernoff-Heffding's inequality. This gives us a bound on how much a sum of a set of random variables differs from its expected value. So let me walk you through this. So the probability that the true mean, so P is the true mean, think of it as, the true probability of a coin showing heads. The probability that the true mean is more than epsilon away from the empirical mean. P bar here is the empirical mean, which is really number of heads divided by m. This is probability of heads. The probability that the true mean is epsilon more than the empirical mean shrinks as e power minus 2m epsilon squared. What this tells us is that the probability that the true mean will computed over m trials is going to very rapidly, the probability of the empirical mean over m trials is going to very rapidly approach the true mean, and the true mean will not be more than epsilon away. And the probability that it's going to be more than epsilon away is this quantity here, e power minus 2m epsilon square. And this is pretty fast because it's exponentially dropping as m increases. As the number of tosses, imagine the coin toss example, as the number of tosses increases, the gap, the probability that the gap is more than epsilon shrinks exponentially. This is an important tool that we will essentially rely on to build up the tail bounds. And notice that this statement is specifically about these things like coin tosses. It's about these independent trials where we have two outcomes. Either you have true or false, heads or tails. In our case, we have something like that. For every example in our training set, either the example is correctly classified or it's incorrectly classified. So it's like a coin toss. So that's going to be our random variable. The more important thing is it quantifies the convergence rate, because it says how fast will this difference shrink. So it shrinks exponentially fast. And this is the tool that we will use for analyzing agnostic learning. And in fact, the whole field, everything here is so heavily dependent on these Heffding's inequality or Chernov's inequality. It's so heavily dependent that, often when people talk about these agnostic learning bounds or other such things, essentially the whole theory is, some people just say we are talking about Chernoff bounds or Heffding bounds. So Chernoff is Chernoff-Heffding bounds. So this particular result is going to be and not just this one, but a family of results around that look very much like these are the building blocks of the analysis of agnostic learning. So let's go back to agnostic learning and we'll see how we can use that result. Suppose the thing that we will do is we will consider the true error D of a hypothesis to be a random variable. It's a random variable. The training error is the empirical estimate of this true error over m examples. So, which means that every single example can be seen as a random sample from that particular true error, that distribution. It's like a coin toss. This is, in the analogy here, this is like the probability of seeing heads, and this is the empirical number of fraction of heads that we see. So then we can ask, what's the probability that the true error is more than epsilon away from the empirical error? We can apply Heffding's inequality. The probability, Heffding's inequality tells us that the probability that the true error is more than epsilon away from the empirical error is less than e power minus 2m epsilon square. I have literally just pasted this in. The first term here is just to make sure that we are all on the same page. This is like in the previous example, we had probability of heads here. And in the previous example, we had here the number of heads divided by m. Here we have the probability of error, and here you have the number of errors divided by n. It's a very similar sort of setting. So are there any questions before we charge ahead with this? Is there any similar approach for multi-class classifier? Yes, there's a lot of, so yes, the short answer is yes. And I can point you to, in fact, I think the class resources, the page for computational learning theory has points to a book by Shai Shalef Schwartz, I think, which gives you which is essentially a theoretical the theoretical perspective on machine learning that kind of that will have pointers. There's another question: what's delta in this case? We'll get there in a minute. So the probability that a single hypothesis has a training error that's more than epsilon away from the true error is bounded not above but below. Right? So the learning algorithm now looks for the best one of many such hypotheses. There are, how many hypotheses do we have? We have size of h, because we are exploring the hypothesis space h. We are looking for the best one, but let's consider any one. So we can ask the probability that there exists some hypothesis whose training error is more than epsilon away is the number of hypotheses, h, is bounded by the number of hypotheses times this quantity here. So this expression is exactly the same as this. This is what we have done here is the union bound. We've seen the union bound in the previous lecture for the consistent classifier case. This is exactly that. The probability that this particular hypothesis has an error that's more than epsilon away is bounded by e power minus 2m epsilon square. Probably that there is at least one hypothesis that has that property is bounded by size of h times minus e power minus 2m epsilon square. This is just saying that there is some classifier. The probability that there's some classifier that is bad is less than this. And this expression here may seem a little complicated, but really what it's saying is the probability that some hypothesis that we are considering inside the set of functions we have has a generalization error that is much worse than the training error. So this is the generalization error, this is the training error. The probability that some hypothesis that we have has generalization error that's much worse, that's more than epsilon worse than the training error, is bounded by size of h times e power minus 2m epsilon square. This is undesirable because this means that there's at least one classifier in the set of functions we are considering that is terrible. And who knows, maybe our learning algorithm, because it is not really great, ends up picking this classifier, and our training error is no longer a good enough estimate of generalization. So the question that what we're going to try to do is, what is it going to take on our part to make this undesirable situation improbable? What's it going to take to make this extremely rare? How rare? This event, I want it to happen. I want this probability to be less than delta, where delta is your small number. There's your answer for where is the delta. I want this quantity to be smaller than delta, and I can now, if I want this quantity to be less than delta, I can do that by saying this thing is less than delta. If the size of h times e power minus 2m, if this is less than delta, then of course this is less than delta. So now we have an expression that does not involve any text and only symbols, so we can apply the usual sort of symbol manipulation. We can rearrange this. I can do that very quickly. I can take log on both sides. So I have log size of h minus 2m epsilon square is less than equal to log delta. I can move things around once again, and that will, so log size of h plus log 1 over delta is less than 2m epsilon square. And now if you move the epsilon down and switch just swap the directions of inequality, you get if m greater than 1 over 2 epsilon square times log size of h plus log 1 over delta. So it's the same game as before. If we have these many examples, if the number of examples we have is more than this quantity, then h, the size of h times e power minus 2m epsilon square will be less than delta. If this thing is less than delta, then this thing is less than delta. But this is the thing inside the bracket here is an undesirable situation, which means what we have here is the probability there exists some classifier that's bad is improbable. But we notice that we have changed the definition of bad here. We are calling a classifier bad if its generalization error is more than epsilon away from the training error. So the probability that we have a classifier whose generalization error is much worse than the training error is less than delta. Why? Because if we have these many examples, then we've just proved it. So let's look at this and try to interpret this. An agnostic learner, it makes no commitment about whether or not f is in the hypothesis class, and let's say it returns the hypothesis with the least training error over m examples. It can guarantee that with probability 1 minus delta, the generalization error is no more than epsilon away from the training error, provided the number of examples we had is more than this quantity here. This epsilon here is the difference between the training and the generalization error. How much worse will the classifier be in the future than it is at training time? Once again, we see that there is a dependency on the log of the size of the hypothesis class. This is again an Occam's razor theorem. It says, in the absence of any information, I prefer smaller hypothesis sets because that will give me smaller m. So this allows us to essentially prove or disprove pack learnability for in the agnostic case when we don't make any commitment whether the true concept is in the hypothesis class or not. What we also have by rearranging this is a generalization bound, which says how much will the true error deviate from the training error if I have m examples. It says if you have m examples, then with high probability, with probability more than 1 minus delta, the generalization error will be no more than this horrible expression more than the training error. This is called a generalization bound. So these are two ways to think about agnostic learning. So we have maybe a minute or two left. So let me very briefly summarize. What we saw so far on last Thursday, we saw this Occam's razor. When the hypothesis space contains the true concept, the sample complexity says, if I have m greater than this quantity here, these many examples, then I can prove with high probability the classifier is going to be good enough. It's going to have error less than epsilon. In the agnostic case, where the true hypothesis may not even contain the true concept, we are paying a little more because we are essentially giving up some information. We are paying a little more. Epsilon has now become epsilon square in the denominator, but the rest of it looks essentially similar. Importantly, in both cases, it seems like learnability depends on log of the size of the hypothesis space. So the question then is, have we solved everything? Is there so what about things like linear classifiers? Where do they fit? What we have seen so far does not even talk about this because we are only talking about finite hypothesis cases. So, okay, let's see. We are at 10:30, so I'll just take this one question. Do we need fewer samples for agnostic learning? Actually, no, we need more samples because remember, epsilon is a small number between 0 and 1, which means here you have 1 over epsilon dependency and here you have 1 over epsilon square dependency. So you need to pay more in terms of sample complexity in the agnostic case, which seems like a natural thing because you are giving up you are essentially not using some information. You don't have some information, so you have to pay a higher price in terms of sample complexity. Okay. Yes, the keyboard was. We are a minute over time, so I'll stop here. And in the next lecture, we're going to consider something that we have completely avoided so far, which is nothing in the theory that we did talks about linear classifiers. We assumed finite hypothesis spaces. What if we drop that assumption? And we're going to build up this really cool theory around VC dimensions and shattering that is going to substitute this notion of log size of the hypothesis class. So we'll talk about that on Thursday. I have office hours today at in 15 minutes. So if you have any questions about anything we saw today or anything in general or about your homework or project, I'll see you there. There will be probably a new homework, most likely end of today, early morning tomorrow. It'll talk about all of this stuff, learning theory and such things. It won't have any programming. It'll be just math. And I'm sure many of you are overjoyed. All right, I will see you all on Thursday. It'll be a PDF.